All right. Um, so I'm going to call this page 0 of our problem set because we kind of worked on it together in class. And we worked on the other pages after that sort of separately. And this is the example I did, but I just want to review it right now. So we start with a free body diagram of the block. We've got the normal, we've got the weight, we've got the applied force, and we've got the friction force right here. Now it says suppose the static friction coefficient is 0.3 and we want to know if the block moves. Again, let's just double check. First, we know this is the mass. So let's get the weight. Oops, sorry. So we know this is the mass. So let's go ahead and get the weight as mass times gravity, which is going to be 6 mass times the acceleration due to gravity, which is 6 times 10, which is 60 newtons. All right. Now, let's calculate the normal force based on the fact that the vertical force is balanced. So I know the normal force is going to try to balance the weight force, and the effect, therefore, is no motion, and that results in the normal force being equal to 60 newtons. True for number 1, but not useful yet. It's useful in question 2. So it says suppose the static coefficient of friction is 0.3. We want to know if the block moves. All right. So we're going to get the maximum friction that we can generate in this system. Okay. So here we've got 0.3. So in other words, let me just back up a little bit. So the maximum static friction is going to equal mu static times the normal force. And in this case, that's going to be 0.3 times the normal force of 60, which is going to end up being 18 newtons. Now, we got to look over here and compare. We can generate 18 newtons of friction to match the pushing force. But we only have 12 newtons worth of pushing force. So what that means is when I push with 12 newtons, I know that the friction force can at least match 12 newtons, which it will do in this case. So that tells me the 12 newtons is balanced by a friction force that in real life ends up being 12 newtons. So once again, just to be clear, this is the maximum friction force I'm capable of generating, but I'm not necessarily going to generate it. I'm only going to generate enough to balance the real pushing force. This is the pushing force, or the pulling force. Here's 12. Friction balances that, so we get a 12 Newton force. Now it says how much force is needed to pull the block so it can move. Let's go ahead and calculate that. We look here, and what it actually ends up being is that the applied force wants to balance the maximum friction force. So when we actually work out this math, we need a force that's bigger than 18 newtons for it to move, which is exactly what we get in problem 4 here. And since we know that 36 is bigger than 18, this tells us it moves. Since we're bigger than 18 newtons of force, just write that better. So we do know it moves. So let's go ahead and do that calculation now. So we know that the applied pulling force fights the kinetic friction, and the effect is that our mass accelerates. So let's actually calculate the kinetic friction force. So that's going to be 0.1 times the normal force, because that's mu kinetic. So that's going to be 0.1 times 60, which is going to give me 6 newtons worth of kinetic friction. Okay. So using that in the equation on the left, we're going to end up getting that the 36 Newton force fights the 6 Newton force, and the effect is that our 6 kilogram block accelerates. So 30 is 6 times A, and so what we're going to end up getting is that our acceleration is going to work out to be 5 meters per second squared. All right, so that's page 0.